Hey guys, welcome back. We got day 32. We're talking about limiting reactants today, also in theoretical and percent yields. This is a big topic. And so we have a reaction here, N2O, dinitrogen monoxide or nitrous oxide, reacts with oxygen gas to make nitrogen dioxide. If you guys notice the balanced chemical equation, there's 2, 3, 4. So there's your mole ratio, 2 to 3 to 4, right? Okay, now, for our N2O here, if we have 3 moles are mixed with O2, 4 moles, your question is, what is the maximum amount of product, right? We're going to actually just do, what's the maximum amount of, I want to use colors, NO2 here, that we can make. And so if you notice, 3 and 4 are different mole ratios than the actual ratio of them, right? Okay, that's just how it works. I mean, if you are the grocery shopper in your household and you are also in charge of preparing food, you don't just buy, like, if you need 4 eggs, you don't just buy 4 eggs, right? Or if you need whatever you need, you don't just buy that amount that comes to your door every day, right? Hopefully you go to the grocery store and buy bigger amounts and then you plan accordingly, right? And so reactants are not present in the correct mole ratio. The one reactant will be consumed first. That's the limiting reactant. That controls everything, all right? And then everything else is in excess of requirements, all right? Now, if we look at this, we have 2 reactants. We have 3.0 moles of N2O. And if we look at what we can make with N2O, we'd have moles of N2O on the bottom, moles of nitrous oxide on the bottom, moles of nitrogen dioxide on top, and those ratios are 2 to 4. So if we have our 3 moles of nitrous oxide, we can actually make 6 moles of product of nitrogen dioxide. If we take our 4 moles of oxygen, right, and we see that moles of O2 on the bottom, moles of NO2 up top, and that ratio is 3 to 4. It looks like we get, what is that, 16 thirds or 5 1/3, 5.3 moles of NO2 that can be produced. So even though 4 moles of O2 is more moles than 3 moles of N2O, O2 is our limiting reactant, right? So this shows you that O2 is the limiting reactant. That means NO2 is present in N2O, is present in excess. Excessive requirements, right? That is, a lot of times I will put LR, I don't know why, I've been using orange for the longest time, but I put LR, limiting reactant, for O2, okay? Because that is then what we will start with all our calculations. Now the next question is, how much non-limiting reactant remains? Because I'm not going to ask you, well, how much nitrous oxide, N2O, remains? Well, that kind of like gives it away, right? I guess it's 50-50 in this case. It could be 0 because it'd be the limiting reactant, right? Okay. Right? And so remember, the limiting reactant is completely consumed. So the non-limiting reactant is N2O. But we start with, right? We start with 4 moles of O2 because that's our limiting reactant. You start with limiting reactant. Start with moles of limiting reactant. And then moles O2 on the bottom, and moles N2O on top, right? And it would be 3 to 2, right? Because if you look at the equation here, 3 moles O2, 2 moles N2O. And so that's 8/3, right? 8/3, or 2.7 moles of N2O consumed or used. Right? So that's how much we use. So since we start with 3.0 moles of N2O and we use 2.7 moles, that means 0.3 moles N2O remain, right? Or we have that much excess, all right? So that's how the limiting reactant is found. You have to figure out both, right? How much N2O can make, how much O2 can make, or how much reactant 1 can make, how much reactant 2 can make, if there's a third reactant, how much that makes, and then you figure out the smallest one. Now, a useful way to determine the limiting reactant. You divide, right, the number of moles each reactant by its coefficient. In the balanced equation. And then the lowest number is the limiting reactant. All right? Well, if we remember, we had N2O, O2, and O2, and it was 2, 3, and 4. And we had 3.0 moles, and we had 4.0 moles. So if we have this situation here, right, this is typically how I do it, right? This is how I do the math. I will take, and I used orange. You don't have to use orange. I used orange for whatever reason. 3 divided by 2 is 1.5. 4 divided by 3 is 1.3. All right? And so that means this is my limiting reactant. Right? And if you need to, the 4 is here, right? We'll do the blue 4, the green 3, right? That's where those numbers come from. And then the coefficients are 2, that's a coefficient, and 3 is your coefficient. Right? So hopefully you know that's where they come from, right? And so that's sloppy on the screen. We'll fix that for you. Right? We have 3 here, we have 4 here, and we're dividing them both by their coefficient. All right. Now, once I do that, once I figure out the limiting reactant, I like to draw a line through that because I want to use this number to start all my calculations. That's where I start calculations. Start calculations with moles of your limiting reactant. That's very important, okay? I don't want to use the 1.3 because I don't want to do that. I already did math. I want to start with the moles. This is just a shortcut to make it easier, all right? You do not have to use it. You can more than happy to do 1, 2, and then figure this one out and go from it. You're more than willing to do that, okay? If you want to do it that way, if you learned that way before and you're comfortable, feel free. This to me saves time, this method, but again, we don't want to use those numbers. We want to use that number. So let's do an example. All right. Suppose 6.54 grams of zinc is treated with 5.47 grams of hydrochloric acid in solution. All right. So we have zinc and HCl. So if you go to a highlighter here, I have that much zinc And we'll do that much HCl. What's the maximum amount of H2 gas that can be produced? So we're looking for H2 here. So how I set this up, I have 6.54 grams of zinc. I have 5.47 grams HCl. And we want to know how many grams here. That's my question. So that's how I start this. Okay. Now, I like that. We gotta go. We got grams. I have mass. What do we need to get to? So we have mass. We gotta go to moles, right? We gotta go to moles, and so we divide by the molar masses, right? The molar mass, and the molar mass is zinc on the periodic table, 65.39 grams per mole. Hydrogen is 1.01. Chlorine is 35.45. So that's 36.46 grams per mole. And so if we do this, I get 0.1 moles of zinc. And we get 0.15 moles of HCl. Now, I didn't check, because I saw the 2, is this a balanced equation, right? There is a 1 for zinc, a 2 for the HCl, and a 1 here and a 1 here. And does that work? Yeah, I think so. 1 zinc, 1 zinc. 2 H's, 2 H's, 2 chlorides, 2 chlorides. We're good. Now, how I find the limiting reactant? I take the 0.1 moles, divided by 1 is 0.1, and take 0.15 moles, divided by 2, it's 0.0, let's call it 0.75. So that means HCl is my limiting reactant, which means I'm going to start my calculations with this. All right? And we are going to ignore that. I want to get rid of it completely, but I want to ignore that. All right? So now, I take my moles of limiting reactant, 0.15 moles of HCl. And let's see here. Moles of HCl here. Moles of H2. Now, it does not say, it says amount. So moles is an amount. I'm going to go to grams just because we started in grams, but it doesn't specify. So if you just go to moles, you could be done. Now, it's 2 moles of HCl, 1 mole of H2. And we know that 1 mole of H2 is 2.02 grams of H2. And so if we do that math, I think we get 0.15 grams of H2. Now, my sig figs are wrong here, because I only have 2 sig figs when I did the math. So I only get to have 2 sig figs in my answer. I bet you that's not the right answer. I bet you it's 1.152, because I bet you there's a 0 here and a 0 here, right? But if I don't write those zeros in, sig figs aren't right, okay? So make sure, I was lazy with the pencil there. If you're lazy with the pencil, I need to have the 0.150 here to make that work. All right. And so then the next question is, what is the non-limiting reactant at the end? So what do we have to do here? Looks like we have to start with our moles of limiting reactant, figure out how much zinc reacts. So we'll take our, that's a highlighter. We'll take our 0.150 moles of HCl. And we know it's moles of HCl, moles of zinc. And we know that it's 2-to-1 from the coefficients in the equation. And then we got what? 1 mole of zinc is 65.39 grams of zinc. And if we do that math, I think 4.90 grams of zinc is used or consumed. So if we start off with 6.54 and we use 4.90 grams, it looks like that would be 1.64 grams of zinc remaining. So that's how we do the limiting reactant. That's it. All right. Now, this problem, typically, if we were talking face to face, I'd say, all right, do this problem, right? Equation's already balanced, do the problem. See what you get, all right? So go ahead and pause me, do it, and then see what you get. All right, let's see what you did. All right, we have 3 moles of hydrazine, right? And if you are like me and like colors, I got 3 moles of hydrazine, which is this one, right? Because it tells you hydrazine is that one right there. Reacts with 2 moles of N2O4 dinitrogen tetroxide, right there. How many moles of N2? All right, so if we do this, I like to do this, N2H4 plus N2O4 goes to N2 and H2O. 2, 1, 3, 4. We have 3.0 moles, and we have 2.0 moles. I like to do that. Do you need to rewrite it? No, but I like to do it. So 3 divided by 2 is 1.5. 2 divided by 1 is 2. So that means we have a limiting reactant right here of hydrazine. And we start with that number. And we just want moles. So we're going to start with 3.0 moles of N2H4. And we'll do our mole ratio. Moles of N2H4. Moles of N2. Coefficients from the equation, 2 and 3. So that's what, 9/2 or 4.5 moles of N2 produced. And that's it. So hopefully you got 4.5 moles on your own. All right. The next topic we're going to dive into is percent yield. All right. Okay. And sometimes the actual amount of product obtained in a reaction is less than expected. I'll pick on my bakers here. If you're a baker, like my wife is, and you're making cookies, and maybe it's supposed to make 24 cookies, but only 20 cookies make the plate, or the cooking sheet. Anybody have that problem? Right? Or if you're making blueberry muffins, and it's supposed to make 12 muffins, and you only get 11 in there because you made them bigger, right? So that's an example of a percent yield. You get 11 out of 12 or 20 out of 24, right? You take a test and you get 19 out of 20 correct, right? That's a 95% yield, right? That's the same thing. So percent yield is equal to the actual yield divided by the theoretical yield times 100%. All right. Now, actual yield in the lab, right? It's measured. Theoretical yield is calculated, which is on paper. All right, so that's what you actually get in lab versus what you should get in lab. Because every time we transfer from container to container, we're going to lose some. That's just the way it works. All right, because if you could transfer from container to container and going back to making muffins or something like that, you wouldn't have to do dishes if you got everything out of the container, the bowl, the mixing bowl. Like, oh yeah, everything's out of there. Yep, there's no molecules left over. We're good. Just put it back in the cupboard. But we know that's not the case. We know there's even ones we can't see, so we have to wash it. Otherwise, we will know that we didn't wash it, right? And so, right, every time we transfer, we're going to lose some. So if you get above 90% yield in a lot of reactions, that's fabulous. Some reactions are only 50% yields, and that's just how they are. Some are less than that, all right? And so, but it just depends. Here's an example of this. Now, uranium 6 oxide plus bromine trifluoride, making uranium 4 fluoride, bromine, and oxygen gas. Now, this would be very dangerous to do and very stupid to do, right? Because this is a method of enriching uranium, potentially. We're not going into much detail, but you don't want to do that just at your house. Plus, bromine is very toxic. You don't want bromine around. Uranium 4 fluoride is a gas. We don't want to be breathing that in. Bromine trifluoride, you don't want to be playing with that either. And to get uranium 6 oxide would be a problem anyway. You probably get some visitors. So do not try this at home. And the reason they do this, though, is because uranium is number 92, weighs 238. But the uranium that goes boom, the nuclear material, even for power plants, is uranium 235. It's a little bit lighter. All right, and so they make it a gas and use a gas centrifuge to try to get rid of the heavier uranium to enrich it from less than 1% to about 3%, I believe, U-235. But we're not going to do that. We're just going to do this on paper. What's the theoretical mass? All right. The question is, what is the theoretical mass of UO4 that can be expected, right? So you have to do these in order. You got to determine the limiting reactant, calculate theoretical yield, and then dispose the actual yield. Your actual yield from the lab was 380 grams, right? What is the percent yield? All right. So you kind of have to, if I just told you that it was 380 grams, what's the percent yield? You still have to do steps 1 and 2, if that makes sense. The percent yield, now, I have to either give you the percent yield or give you the actual yield. I have to give you one of the two, right? So in this case, we gave you the actual yield. You have to calculate the percent yield. I can give you the percent yield and calculate the actual yield as well. Both are fine, but I have to give you one. Otherwise, you wouldn't be able to do it. All right, so I'm going to, again, rewrite. I like my colors. You guys, maybe you don't like your colors. I like my colors because they pop out to me. You don't have to. I like them. All right, so we're starting with 357 grams and 357 grams. So we have grams. Hopefully by now we have to go to moles, right? So uranium, again, 238.03 plus 3 oxygens at 16. I get 286.03. And if we do that math, 357 by 286.03, I get 1.25 moles. For bromine trifluoride, bromine is 79.9 and fluorine is 19. 3 of those, I get 136.90. So if I do that math, it looks like I get 2.61 moles. All right, and so if we do this, I get 1.25 moles divided by 6, and I get 2.61 moles divided by 8. And so 1.25 divided by 6, I get 0.21 and 0.33. So that means your uranium 6 oxide is a limiting reactant. So I'm going to take this number here and erase those. All right. And so I'm going to start with my 1.25 moles of uranium 6 oxide. Try it real quick. I want you to try it. Pause me and try it, or just try it right now, and then we'll go from there. All right, hopefully you got it. And let's see, how are we doing? Oh, man. I got on the bottom here, I have to have moles of UO3 at top, moles of UF4. And we know our ratio is 6 to 6. Now, I would continue to write 6 to 6. Just because now if I look back at this in a month, I'll know exactly where those 6's come from. If there's one there and it's the same color, right? It's not color coordinated, it's going to be very hard to know where those came from. But if I see the 6 and 6, I will know exactly where they came from as the coefficients. I would recommend doing that. When you do the calculations, you just ignore it and that's fine. But right now I'd leave it 6 and 6. 1 mole of uranium-4 fluoride, I got that to be 314.03 grams of uranium-4 fluoride. And so I get, as a theoretical yield, 392.54, so 393 grams of uranium-4 fluoride. All right, so this is my theoretical yield. How do I get the percent yield? The actual was, it's 380, right? 380 grams. That's from the problem. Right? Tells us in the problem right here. 380 grams. The theoretical was 393 grams, and that was the calculated, times 100%. All right? And so if I do that in my calculator, you get 380 divided by 393 times 100%, I get 96.7. Perfect. That's great. Calculated is horrible here. There we go. All right. Hopefully that works. Now, this is the last problem. I want you guys to try it. So go ahead and pause me, try it, and then come back. And I'm going to do it with you. All right. Hopefully you did it. All right. Is it balanced? Yes. So a little shortcut for a test, for example. I would just, gold, I have 100, right? I have 402 grams of gold. So I'm just going to, here we go, snap them. Right? I have 402 grams of gold. I have 150 grams of nitric acid and 350 grams of HCl. Looks like a weird tube. There we go. So this is actually aqua reagent, which is very nasty stuff, but it will dissolve gold because most, right, it oxidizes it and a lot of fun. All right. This would be a very expensive way to make water because they want us to know what mass of water can be formed in grams. Very expensive way, but let's do it anyway. All right. So gold is 196.97 grams per mole. So 402 divided by 196.97, I get 2.04 moles of gold. Nitric acid, well, you have 1.01 plus 14.01 plus 16. I get 31.02 gram. Oh, times 3. 16 times 3. Excuse me. 6302. That's better. So 150 divided by the 63.02, I get 2.38 moles. HCl weighs 36.46 grams per mole. And so if we do this, the 350 divided by the 36.46, I get basically 9.60. All right, so now limiting reactant time. 2.04 divided by 1 is 2.04. 2.38 divided by 1 is 2.38. 9.6 divided by 4. I get 2.4. So that means gold is my limiting reactant. So we're going to start with this number here. Cross those off. All right. So I'm going to take my 2.04 moles of gold. And we know that moles of gold versus moles of H2O. And we have 1 and 2. And then we're going to mass. So 1 mole of H2O, 18.02 grams of H2O. All right, now hopefully you've been doing all these molar masses now, and some of them you recognize, all right, because you're calculating a lot. All right, so if we do the 18.02 and we're multiplying that by 2 and 2.04, we get 73.52, and I really only have 2 sig figs, so it's 74. All right, so that is the limiting reactant. And that is it for the chapter. All right, and so hopefully that works for you guys. If you have questions, reach out to me. All right, give me an email. Do lots of practice. And we will see you in the next video, guys. Take care. Bye.